Welcome to Analytic Methods for Lawyers. This video is on distributions to know and love. It's like the opening credits to a TV series in the sense that there are a lot of characters, you're not quite sure who they are, how they fit together, whether they're good guys, the bad guys, but this is simply to identify some of the main characters for you, so when you see them again, it's not a complete ambush. And my hope also is that having all of this information in one place will be useful. You can go back and study this section of the video if you get confused later in the course. Okay, let me just start off with a little code note. You're going to see some functions, reshaped graphics grid. You don't really know how they work. All you need to know is that they make the graphics look a little bit prettier. So let's close that up and move onwards. All right, let's look at the main distributions we're going to be studying. The first is probably the simplest distribution, the Bernoulli distribution. It's basically modeling a coin flip, although you get to set whether it's a rigged coin or not. It can output a 0 or a 1. And so if I ask, it has a single parameter p, which is the frequency that things come up with ones. And we can see what's the distribution domain of it. And it's the span from 0 to 1. Span just means everything, every integer in the span inclusive. So we can see with discrete plot and a table how the PDF of the Bernoulli distribution varies depending on the frequency of heads. And if we look at that, we'll see an example. When the heads frequency is 0.2, well, 80% of the time it comes out a 0 and 20% of the time it comes out a 1. If it's 50-50, then you see it 50-50. If it's 80% heads, it's 80-20. Really nothing very hard here. Single parameter distribution, and that parameter is the frequency of heads. It outputs zeros and ones. The Bernoulli distribution, even though it seems kind of trivial, is one of the building blocks of the binomial distribution, logistic regression, and lots of other things. So it's simple but important. What's a binomial distribution? A binomial distribution is a sum of Bernoulli distributions. It basically asks the question, given that I roll my coin n times, and I know that my coin has a heads frequency of p, what's the total number of heads I'm going to get? So if I have a binomial distribution with a first parameter of 10, that's the number of rolls or draws, and p is the frequency of heads. We can ask what's the distribution domain. Well, what could happen? Let's see. I could roll and never get a head. I could roll and they could all be heads. And so it's the span from 0 to 10. We can look at a plot of the PDF of the binomial distribution when it has 10 rolls for different frequencies of heads. And you can see right here what that looks like. When the heads frequency is low, you're probably going to get 2 heads. You might get 1, you might get 3. Very unlikely you're going to get 6. When the heads frequency is 5, you're most likely to get 0.5. You're most likely to get a result of 5, could get a result of 7, could get a result of 3. But you can see what the probabilities are. And finally, we can jump down here. If the heads frequency is 0.9, you're most likely to get 9 heads. You could conceivably get 6. Getting 2 heads, you'd have to really worry about what kind of coin this is. All right, so again, we'll see the binomial distribution and logistic regression. Multinomial distribution. Multinomial distribution is kind of like the binomial distribution, but it handles coins that have more than 2 sides. That is, supposing we have a coin that has 3 sides somehow. And what we're interested in is what's the probability of the head, the tail, and I don't know, the belly button. So we parameterize this much in the same way that we parameterize the binomial distribution. The first is the number of rolls or flips of our imaginary coin. And instead of having one number that tells us the number of heads, we have 3 numbers that tells us, in this instance, the probabilities of each of the 3 outcomes that the coin can provide. So these really should sum to 1. What's the domain? The domain are three numbers, each of which can range from 0 to n. We might get all heads, all tails. We might get all heads. We might get all belly buttons. We'll just have to see. Remember that, here's an example, by the way. Let's use a concrete example. Here we have a distribution with 10 flips, 40% probability that it'll come out let's call it a 1, 30% a 2, 20% a 3, and 10% a 4. And you'll see how we'll just name this multinomial 4. Let's say, hey, factory, start producing. Remember, that's what random variate does. It's a command to the factory to get its act together and start spitting out stuff. So I say I want 20 draws. And so you'll see, what does this mean? That means we have 4 of the first category, 2 of the second category, 3 of the third category, and 1 of the fourth category. And what's the second draw? The second draw was 5 of the first category, 4 of the second category, 0 of the third category, and 1 of the fourth category, etc. Okay? Now, visualizing the results of a multinomial distribution it's not that simple, but what we could look at are the distribution of the marginals. Remember, marginals are taking one dimension of a multidimensional distribution. And here I'm going to have a little table that's going to generate the 4 marginals of the 4 outputs that our distribution can have. And you can see that actually each of the marginals are themselves binomials, and we kind of know already what those marginals look like. They're going to look something like this, although the precise look of the PDF is going to depend on the precise head frequency. But that's one way to begin to visualize the outputs of a multinomial distribution. We could also look at all combinations of outputs. Supposing I want to look at the first and third output, and I want to know how frequently would the first output be 4 and the third output be 3? Or how frequently would the first output be 5 and the third output be 3? Or how frequently would the first output be 7 and the second output be 0? And here we can use a 3-dimensional histogram to actually visualize this. And this is going to show us in a moment. Here's the first and the second. You'll notice that they can't be bigger than 10. Here's the first and the third. Here's the first and the fourth, the second and the third, all possible, the second and the fourth, and the third and the fourth. So there are multiple marginal distributions of a multinomial distribution if you don't collapse them all down to a single. Like here, we just were looking at a single dimension. But what if we want to look at multiple dimensions together? You might ask, why is this important? And the multinomial distribution turns out to be crucial to understanding the Fisher exact test for categorical variables that we will see later in the course. Okay, so discrete uniform distribution. The discrete uniform distribution models a die that can have any number of sides you want and that can output integers, whatever integers you want. So for example, here I'm looking at a discrete uniform distribution which can output 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And what we're going to be looking at is we're going to be looking at a discrete plot of first the PDF, then the CDF, then the survival function, then the hazard function of this distribution. So here's what our PDF looks like. All the possibilities are equal. Here's what our CDF looks like. If you ask me what's the probability that the output of our distribution is 15 or less, well, that's 100%. If you ask me is it at 4 or less, it's going to be 0. And it just steadily climbs in a linear way between those two extremes. The survival function, you remember, is simply 1 minus the CDF. So that's kind of we could almost flip this over to see it. And the hazard function, you remember, is the PDF divided by the survival function. And that's a picture of the hazard function of the discrete uniform distribution. Beta distributions. Beta distributions are very interesting creatures. They take two parameters to define the member of the firm, to define the factory. They output numbers between 0 and 1. What's neat about the beta distribution is its flexibility. Its PDF, which I'm about to show you, can, depending on which firm you're looking at, be flat, it can be bell-shaped, it can be upward sloping, downward sloping, or an upside-down bell. So let's take a look at that. And we're going to see, there's our graphics grid. Okay, so if the parameters are 1, 1, it's flat. If the parameters are 3, 7, it's sort of skewed off to the left. If the parameters are 7, 3, it's skewed off to the right. If the parameters are 1, 4, it goes down like this. We're going to see this particular parameterization when we look at risk aversion and something called spectral measures. It could be go upward sloping if the parameters are 4, 1. And finally, if both of the parameters are fractions, positive fractions, you get an upside down distribution where you're very likely to get values at the extremes, but very unlikely to get anything in the middle. So that's our friend, the beta distribution. The uniform distribution. I mean, if you're looking for a simple uniform distribution, a simple continuous distribution, the uniform distribution is about as easy as you get. You just set the bounds on it, and you say any number within those bounds is equally probable. So we can take a look at its PDF, CDF, survival function, and hazard function. And there's its PDF. This one is for a uniform distribution that has its low bound at -1, its high bound at 3. Here's its CDF. It's a line going up from 0 to 1. Here's its survival function going down in a mirror fashion. And here's its hazard function where it goes up because the survival function starts to get very low. That's our denominator. And the PDF stays constant. That's our numerator of a hazard function. So, the normal distribution, okay? The normal distribution, which, by the way, you will sometimes hear called the Gaussian distribution, which is sometimes pronounced Gaussian distribution, which makes it even more confusing, is perhaps the most important distribution in statistics. Many, many natural phenomenon can be well modeled by a normal distribution. There's something called the central limit theorem, which basically says that certain distributions will converge to a normal distribution. So you need to know it. Typically, the way you parameterize the normal distribution is with two parameters, its mean and its standard deviation. The mean you may know is think of as the weighted average. The standard deviation you can think of as a measure of how spread out it is. And so other things you should know are when people speak of the normal distribution, usually they mean a normal distribution with a mean of 0 and a standard deviation of 1. So let's take a look again at some normal distributions. Let's use a manipulate to help visualize our normal distributions. Okay, so here's our PDF, and you can see as I shift the mean of the normal distribution, its center moves to the right. As I decrease the mean, its center moves to the left. Let's kind of get it back to the beginning if I can. There we go. As I increase the standard deviation, the amount in the tails kind of gets fatter. As I decrease the standard deviation, you'll notice it gets thinner and the peak gets higher. So that's our friend, the PDF of the normal distribution. The chi-square distribution. Okay, chi-square is actually a transform of the normal distribution. If you remember an earlier talk, I talked about transformations of distribution. Supposing you took the output from the normal distribution, and by the normal I mean n0, 1, and you squared the output. What would the distribution of that value look like? And the answer is, well, that has a name. It is the chi-square distribution, and with 1 degree of freedom. If I took the output of n independent normal distributions, and I summed up the squares of their values, that output would be a chi-square distribution with n degrees of freedom. So let's use a manipulate here to take a look at our friend the chi-square. Here's the chi-square with 1 degree of freedom. 2, 3, 4. Let's go out to 10, go out to 15. And so now you know what the survival function of a chi-square distribution looks like. Gonna turn out that the survival of a chi-square distribution is critical to hypothesis testing, particularly in something known as analysis of variance, or ANOVA. That's chi-square. Next member of the cast, the logistic distribution. The logistic distribution is a lot like the normal distribution in that its PDF is bell-shaped. One of the reasons people like the logistic distribution is that its CDF, it has a very simple expression form. It's just 1 over 1 plus e to the negative x. So you do have to cope with that little pesky e thing, but otherwise it's a pretty simple formula. It's nothing like, for example, the CDF of the normal distribution, which has this IRF-C in it, and who the heck knows what IRF-C is. In fact, let's just see. Will it even tell us? No, it's not even going to tell us what IRF-C is. All right. One thing we could do is see, hey, what do these parameters mean? It turns out 0, the first parameter is the mean, and the second parameter has something to do with the width, but it's not the standard deviation. If I say, what is the standard deviation of a logistic distribution with parameters a and b, it is not going to give me b, it's going to give me b times this factor pi divided by the square root of 3. So it's clearly proportional to the standard deviation, but it's not the same thing as the standard deviation. Let me just say that this form is sufficiently important that there's a Wolfram Language function that gives you this form without having to think of it as being part of the CDF. If I say, what's the logistic sigmoid of x, and expand that function, this is what I get. So there are 2 ways of writing this expression. One is to think of it as the CDF of the logistic distribution with first parameter 0 and second parameter 1. The second is just to think of it as a standalone function called logistic sigmoid. Okay, we can see what a logistic distribution looks like. And here, I've made a handy-dandy manipulate. We can look at how the PDF shifts as I shift the mean. We can see how the PDF shifts as I shift the width parameter. Let's look at the CDF. There's the CDF of, let's go back to our sort of canonical level here. Let's make the width parameter 1, and our mean, let's set that back to 0. And I forgot, actually, you know what you can do? You can click on this and say initial settings, and then it'll just go back. All right, and we don't need to see those anymore. So with the CDF, you can see as I switch the width that S is going to get tighter, corresponding to a lower width. If I increase the width parameter, then it's a more gentle ramp. And if I move the mean, the sort of inflection point where it changes from going up rapidly to going up slowly will move now to the left, now to the right. We can look at the survival function, but you know, I hope by now, that that's just going to be 1 minus the CDF. So if it's 0.2 at about, what is that, negative 1.9-ish, maybe negative 2, it should be about 0.8 when I flip it. And lo and behold, it is. Good. So that is the logistic distribution. We're going to see the logistic distribution when we do the logit model fitting. It's used in machine learning and statistics extensively. The student t distribution. Okay, so the student t distribution is named after its anonymous discoverer who did it as like a homework problem, and just signed himself a student. Sometimes people omit the student and it's just called a t distribution. Either way, it looks a lot like a normal distribution, but it has fatter tails, and it has a single parameter, and that parameter is called its degree of freedom. And we're going to see this term degree of freedom used throughout the course. Just know that it just means it's a parameter of a distribution, and for various reasons, people happen to call that parameter a degree of freedom. They could call it a Fred, they could call it a hot dog. It's all the same thing. It's just that it happens to be called a degree of freedom. So here we are, and we're going to start increasing the degree of freedom, and you can see it's kind of getting tighter around the center, although as I keep increasing it, not much happens. But if I lower that degree of freedom parameter down, you can kind of see it getting fatter around the tails. So that's our student t distribution. Okay, where are we going to see it? We're going to see it in trying to find out if two samples are drawn from distributions with the same mean or the different mean. All right. The multinormal distribution. So we're now going to look at a multivariate continuous distribution. And multivariate distributions, you remember, don't just produce one number as an output or one thing as an output. They simultaneously produce multiple things. So how do we define a multinormal distribution? A multinormal distribution has two types of parameters, but they may contain more. In fact, they likely do contain more than one number each. The first parameter is a vector. It's a list of numbers, and its values are the mean of each output from the distribution. So that if the distribution has two outputs, and the mean output of the first number is 3, and the mean output of the second value is -1, then that parameter is going to be 3, -1. The second parameter is a little bit complicated. It's a matrix. If it's producing 3 outputs, it's a 3 by 3 matrix. If it's producing 7 outputs, it's a 7 by 7 matrix. Not all the matrices are permissible. They have to be be symmetric, meaning that if I flip the rows and columns, I'd get the same matrix. And they also have to be something obscure called positive definite that I won't define here. But what I want to show you is this second parameter basically describes how the outputs relate to each other. They may not be completely independent. That is, knowing the value of the x value may give you information on the likely distribution of the y value. So that's what you're being told essentially by that covariance matrix that forms the second parameter of the multinormal distribution. Let's take a look here actually at the PDFs of two multinormal distributions. And you'll see that their first parameter is the same, but their second parameter has the same numbers in the diagonal of the matrix, but the off diagonal here is negative, and the off diagonal here is positive. You also notice these matrices are symmetric, as I told you they needed to be. So what does this mean? This means that there's a positive correlation between the x and the y value. So you're not going to see a lot of situations where the x value is high and the y value is low, or the x value is low and the y value is high. Whereas here, because there's a negative correlation, you are going to see instances in which where the x value is low, the y value is low. And what you're not going to see actually are situations where the x value is high and the y value is high. So hopefully that gives you a feeling for what that second parameter is about. It's about how the outputs of the distribution relate to each other. What's a fun thing we could do? We like fun. Let's make a movie. And what the movie is going to show you when it's done is we're basically showing how the contours change. See those contour lines there? How do those contour lines change as I simply change that off-diagonal element in the covariance matrix? And you can see the ellipses kind of stretching out. We shrink to a center as it gets to 0, and then we have an ellipse going the other way. So that's our one way of thinking about a multinormal distribution. I think I'm going to let you read about the digression on covariance matrices and not present that in this video. Okay, multivariate t distributions. So we need this for multiple regression to understand what the error terms are going to mean. And just like we can have a multinormal distribution, we can have basically a multivariate t distribution. It's the same concept with the parameters. The first is the mean, and the second is how do the outputs relate to each other. In this instance, we have an x and a y. How do they relate to each other? So let's take a look, and it's the same deal where when this number, this off-diagonal element is positive, we see that when x is positive, y tends to be positive. When this off-diagonal element is negative, when x is positive, y tends to be negative. What else could we see? We're going to make what's called a flip view here. And watch this. Flip, flip, flip. Okay, so this third parameter, the multivariate t distribution, has a third parameter which the multinormal distribution did not have, and it sort of has the same role as it did in the regular t distribution. It's going to tell you how fat the tails are. So now it's 1. Now it's 16, tails are fatter. Now it's 32, it didn't really get much fatter. So it seems to kind of peter out as you get up to high degrees of freedom. Okay, as I said, the distribution of regression parameters in a linear regression ends up relating to a multivariate t distribution. So you ought to have some idea what the multivariate t distribution is about. Okay, let's look now not at specific distributions, but at types of distributions or derived distributions. So the first one I want to talk about is an order distribution. Supposing you take multiple draws from a distribution. Maybe I have a die and I roll it 5 times, and I then sort those results from lowest to highest. And I want to know what is the distribution of the second lowest value, or what's the distribution of the third highest value. These sort of distributions are called order distributions. So let's take a look at how we write it and then illustrate what it looks like. Supposing I have a discrete uniform distribution. This is our friendly die, 1 to 6, and I have 3 of them. And what I want to know is what is the distribution of outputs of the middle value, one not too high, not too low. So we can compute that. There it is. And I can say, let's get the PDF of that. And there it is, some hideous expression. But I could say, hey, let's make a discrete plot of that. And you can see that it looks like 3 and 4 are equally probable, 2 and 5 are equally probable, and 1 in 6 are equally probable as the middle value. So we've created another distribution out of a basic distribution here, and this is called an order distribution. Let me give one more example just to clarify it. Supposing I had a binomial distribution and it involved 6 rolls, and the probability of getting a 1 on each roll was 0.25, and I wanted to conduct that experiment 10 times. And what I was interested in was the third highest value. That's how I'd write it. Okay? And we could say, what's the PDF of that? And it would tell us it's this ghastly thing. Okay? We'll see order distributions again when we look at settling lawsuits. It turns out that they are very helpful in figuring out the values of lawsuits. Okay, let's get rid of this and move on to categorical distributions. Categorical distributions are ones in which the outputs are not numbers, rather they're categories. So imagine a factory that can produce 3 colors, blue, brown, and green, and it does so with frequencies 0.6, 0.3, and 0.1 respectively. Here's how we could write it. Categorical distribution. Here are the possible factory outputs. Here's the probability of any particular output. So you'll notice there are certain things you can do with categorical distributions and certain things that you can't do. You can't compute a mean because how do I average blue, brownness, and greenness? And I can't. And similarly, I can't take the CDF, survival function, or quantile of them because those require the outputs to be numerically ordered. The CDF means that you're saying that, hey, a certain percentage are less than or equal to this value. But what does it mean to be less than or equal to brown? So, as I think I mentioned in a prior video, the one thing you can do is use rarer probability. You can ask yourself, hey, I got a brown. What's the probability that I would get an output as weird as brown? And it turns out, well, it's actually that 30% plus that 10%, so it's 40%. What's the probability? So we can compute that, and we can compute the probability of getting a brown or a green. Let's look at that. All right. And so you can see that the rarer probability is equal to the probability of those, the sum of the probability of those items that themselves have an equal to or lesser probability. You can also get additional information out of a categorical distribution, and we're going to use the information function, and we're going to say, hey, would you please tell me the categories, domain elements, probabilities, probability array, and probability table of the cat distribution. And so here we are. We're going to learn, here are its categories, here are its domain elements. Here's an association associating with each domain element a probability. Here's just the numbers that correspond, and here's a pretty table that corresponds to it. You can have multivariate categorical distributions. Here's one in which it outputs maybe eye color and handedness. And so the second argument to the categorical distribution is basically the joint probabilities. So this 0.2 is the probability that I'm going to be blue-eyed and left-handed. This is the probability I'm going to be blue-eyed and right-handed. This is the probability I'm going to be brown-eyed and left-handed, etc. Okay? So we can have a multidimensional categorical distribution. You can see by pressing this plus button, I get certain information on the probabilities. I can ask it rarer probability questions. I can say, hey, I'm brown-eyed and left-handed. Is that something really weird, or is that, there are lots of things people can have. And it tells me, well, it's not super common, but it's not super rare either. All right. We can, again, use information on a multivariate categorical distribution to get all sorts of information out, including the probability array and probability table. We're going to be using categorical distributions a lot because social science and legal data often doesn't produce numbers. It's just sort of things. All right, product distributions. Product distributions are you take two distributions, you assume that their joint probabilities are independent of each other. That is, knowing what the outcome from one of the distributions is doesn't help you figure out what the output from the second distribution is going to be. And so the way you basically get a given probability is you just multiply the probabilities together. So if I have a discrete uniform distribution on 0, 1, a discrete uniform distribution on 1 to 6, this is asking me basically, hey, what's the probability that you're going to get a heads and a 6? And that's for a fair coin and a fair die, that's simply 1/2 times 1/6. So I can ask it to compute the PDF of a product distribution, and it's going to tell me, hey, it's 1/12, so long as your die roll is between 1 and 6, and your heads roll is between 0 and 1. Otherwise, it's 0. Product distributions are very useful because we often have events that we want to model as statistically independent. Marginal distribution. I believe I talked about marginal distributions in a prior video, but let's look at it again. A little repetition never hurt anybody. So let's look at the distribution of eye color in that Cat2 distribution that looked at eye color and handedness. Remember, here's our Cat2 distribution where we're looking at eye color and handedness. Supposing I say, look, I don't care what hand they are. I want to know what the distribution is of their eye color. So that's simply asking for the first marginal distribution. And it produces another categorical distribution in which we have the probability, each of the probabilities there. Instead of clicking on the plus sign, I could say, hey, could you tell me the probabilities of that? Remember, percentage means that last thing, and it's going to tell us what it is. Or we want to know, look, I don't care about what your eye color is. I want to know about your handedness. And so we get a different categorical distribution, and it's telling us the population is 33% left-handed and 67% right-handed. Okay? We can get that programmatically. What else can we do? We can get marginal distributions on a continuous distribution. Here's our multi-normal distribution again, and we've recovered the marginals. By the way, you can't necessarily go backwards. That is, I can't say, get me the marginals of a distribution, and then let me take the product distribution of the marginals and say that that is the original distribution. That is generally not true. It's only true if the original distributions were uncorrelated. But if there's any correlation between the multiple outputs of the original distribution, this business of taking the marginals and then taking the product, you're going to lose all of that associational information. So, why would you ever take marginal distributions of, say, a multi-normal distribution? Precisely to see, in some sense, whether there was any association between the two outputs, between the multiple outputs of the original distribution. So we're going to be using marginal distributions and product distributions a lot in our discussion of hypothesis testing. Okay. Product distributions put distributions together and basically say, I want the components to be independent of each other. Copula distributions say, no, I actually want there to be a correlation structure between the outputs. So to create a copula, what you do is you set forth the underlying distributions. This is the distribution of the x value, perhaps. This is the distribution of the y value, perhaps. And you say, I want to tie them together in this way. This is called the kernel of the copula. Here we're telling us, Mathematica, what is the type of kernel we're using, and then that kernel may need parameters to more specifically define itself. Here we're giving it a covariance matrix, actually, that's going to tie the output from the beta distribution with the output from the uniform distribution. So let's actually make that copula, and now let's look at its PDF. And wonder a little, there we go. Okay. So we've now tied these two distributions together. You can see that it does seem to be some correlation, positive correlation, between the beta sort of component between 0 and 1 and the uniform component between 3 and 5, so that it would be quite common to get a higher than usual first value output, the beta value output, and a higher than usual value from the uniform distribution, but it wouldn't be very common to get a high beta and a low uniform output. And that's because of this positive correlation that's in the covariance matrix here. So those are copulas. You can get the distribution domain of a copula, and you can get the marginals of the copula. But remember, precisely because, in fact, let's do a wild experiment here. Let's take the product distribution of those two marginals out. That's 161. Okay, and now let's take the, let's just plot the PDF of that. So let's just borrow this code right here and substitute in PDI. And let's see what happens. And we get a disaster. Okay. What we want to do, right, is we want to say, what is the PDF of the PDI evaluated XY? And you see how it's no longer, the outputs aren't correlated with themselves anymore. Whereas here, they were correlated, and this is because by taking the marginals and then producting them back together, I lose the very correlation structure that I intended to create by using the copula in the first place. Okay. Little footnote on copulas. They were very big, still are very big in the financial community, and some people blame the housing and financial crisis of the early 2000s on people not really understanding how copulas work. All right, truncated distributions and censored distributions, we have seen those before, but a little repetition again may be useful. Here we can see what a truncated normal distribution looks like. Here I'm moving the left truncation point leftward, so we're sort of getting more of the distribution. Here I'm moving the rightward truncation point to the right. You'll notice that when I have a truncated distribution, if I look at the CDF, it's continuous. There are no jumps in it. Whereas with a censored normal is going to have jumps, because basically any value that used to come out that was less than 1 is now being pushed to being 1. And so there tend to be large amounts of values kind of at the points of censorship. Remember, censorship is basically fixing the output from a random variable, and so you end up with lots of instances that exactly equal the fix. All right, and here's a manipulate that lets you visualize the PDFs and CDFs of, what are we looking at here? A censored distribution of a binomial distribution, okay? So if I censor it, the low censoring point here, then we get this big jump at the CDF. Okay. Time for a refresher on transform distributions. Remember, a transform distribution, you take the output from the factory and you run it through another deterministic function, and that changes the value that it produces. So if we take a uniform distribution on the interval 0 to 1, and we now transform it by multiplying that, that output by 3, we're going to get a different distribution, and it's the uniform distribution on the interval 0 to 3. Or here, if I take the output from a normal distribution and I square it, anyone remember what I get? Chi-square distribution with 1 degree of freedom. What if I take the output from a normal distribution and I take that to the e power? That's what x to the x means. Anyone remember what I get? And I get the log normal distribution with a first parameter of 0 and a second parameter of 1. But as I mentioned, what if I take the output from a binomial distribution and I divide the result by 10? Does that have a name? And the answer is no. It's just a transform distribution. But I can still say, hey, transform distribution, start making stuff. By using the random variate command, it will start to make stuff. And I can use my usual functions on this more general transform distribution. I can find out what its PDF is and what its CDF is. Okay, so it's time to look at something new, which is a data distribution. Two types of data distributions I want to look at: an empirical distribution and a smooth kernel distribution. So supposing I just know that, well, 50% of the time I get zeros, and 20% of the time I get 100, and 15% of the times I get 250, 12% 500, 3% 1,000. And I want to just represent that as a distribution so I can do things like, say, make stuff from that, or what's your PDF. I just wrap that relationship in empirical distribution in the Wolfram language, where the domain elements go to their probabilities, and I get a species of data distribution called an empirical distribution, and I can do the usual stuff like say, hey, make me 1,000 out of you, and let's count up what we have. And it's roughly what we thought originally. I said about 50% are zeros, and that's about 50%. But these are random draws, and so it's not going to exactly reproduce those probabilities. In some sense, that's the whole point. A smooth kernel distribution is like the empirical distribution in that you tell it what you've seen. I've seen one of these, 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 and it will then produce a distribution that can produce basically any value anywhere between 0 and 1,000. In fact, it can even go a little past 0, a little past 1,000, it can go a little past 0, but it can produce values in between. So if you have a situation where these are just examples of things that you might get, but you recognize perfectly well, you might get a 700 or a 723 or a 257.14, then you might want to use a smooth kernel distribution. There's one, and we can see what does its PDF look like, and you can see that it seems to sort of be focusing on this lower range more so than the higher range, because there weren't, the 500 and the 1,000 were kind of spread out. So that's a smooth kernel distribution. A learned distribution. Okay. A learned distribution is something that has come into play since machine learning got well involved. And the idea is you see a bunch of data, you're not exactly sure what generated that data, but you think it's some statistical distribution in which things are correlated with each other, but you don't know how. And what you want to do is to represent that as a distribution so that you can then command more instances through the random variate command. So let's actually make some data. Now, in the real world, we would never see this process. This is nature, this is God, this is some evil scientist creating data for you. So let's do that. All right, we've got lots of data. And now I can say, let's look at the plots. All right, So that's what it looks like, but I'm not sure what this is what I would see. I wouldn't see the process that created the data. I would only see the data itself. And so I might now want to know, could you produce a distribution so that when I ask you to, you can produce more points like this, so that I wouldn't expect you to be producing a point like this or like this, and I would very much expect you to be producing a point in here, maybe out here, maybe out here. Okay, so this is something that's very useful. If any of you have seen the website thispersondoesnotexist.com, you're going to see a more sophisticated version of a learned distribution, where basically it's learned a distribution of human faces. And so you press a button and it produces something that is face-like, but that may not have been in the original data. Okay? So let's run learn distribution on our simple data. And it's actually going through a neural network to do this, I believe. And it's coming up with a model, and it's actually saying, hey, we can approximate this with a multi-normal distribution, which is interesting because that's actually where it came from, although it wasn't told that. And now we can tell it, hey, I command you learn distribution to produce 1,000 examples, and let's just plot those. So if you look at this scatter plot, looks a lot like this scatter plot, but in fact, none of the points are the same. They're all new points. And if you don't believe me, let's see if the intersection of the original points with that produced from the learned distribution has any overlap. And if it says true, or you get actual items, I'm in big trouble. But fortunately, it does not. Okay. Other distributions we might at some point see: a triangular distribution. A triangular distribution is sort of a species of a uniform distribution, but has a triangular PDF where you set forth what's the minimum, what's the maximum, and at what value in between the minimum of the domain and the maximum domain is the probability maximized. Exponential distribution. The exponential distribution is the transform of the uniform distribution. Here's the transform that you use. Here's what a CDF of an exponential distribution looks like. Here's what the hazard function of an exponential distribution looks like. It happens to model some physical phenomenon very well. If we were doing a course in decay of radioactive materials, we would be very interested in the exponential distribution. Log normal, we've seen. Many phenomenon in the world, sort of economic world, tend to be log normally distributed. Amounts of insurance claims, medical claims, a lot of things in sort of human behavior. The stock market returns tend to be log normally distributed. So here's what a log normal looks like. You'll notice that I am scaling it, scaling the x-axis on a log 10 basis, but I'm not scaling the y-axis. If I didn't scale the x-axis, then it looks very skewed, but if I scale the x-axis, it looks a lot more normal. And you can see here I'm increasing the spread of the log normal distribution. Here I'm fiddling with its mean, moving it to the right, moving it to the left. Okay. There's a second way of parameterizing the log normal distribution that I prefer, in which the first parameter is the mean of the distribution, and the second parameter is a fraction of the median as a fraction of the mean. So let's take a look at this in action. Here we've got our same log normal distribution. I can wiggle the mean, moves to the right, moves to the left. But here I'm going to change what fraction of the mean is the median. And as I move this to the left, you can see that let's do this on a let's do it this way. You can see what's happening is that an awful lot of the action is piling up at the left end, whereas if I set the mean to be similar to the median, then our log normal distribution is somewhat less skewed. in any event, that's an alternative parameterization of the log normal distribution. I present it here because it's more convenient, I think, for a lot of what we do. And just to remind you that there are multiple parameterizations, different ways in which you can describe the same actual distribution. The F ratio distribution. I saved this for last, when you would be most ready to see anything. It is a ratio, okay? It's basically a ratio of two other distributions. So, supposing you take an output from a chi-square distribution with n degrees of freedom, and you call that the numerator, and we divided that number by the degrees of freedom, and we took the output from a chi-square distribution with m degrees of freedom, and we divided that by m, and we called that the denominator. And we then said that quotient, that sort of nested quotient, had a value. It's going to have some value, and we called that the F value. This F value will be distributed according to the F ratio distribution. So here's an example, actually, if I just did it, where I took the numerator had 4 degrees of freedom, the denominator had 3 degrees of freedom. I produced 10,000 of them. And now let's do a quantile plot of those values against something called an F ratio distribution with first parameter 4 and second parameter 3. And so it's pretty good. It's pretty close to the line that you would get if it were exactly the same thing. And we're sampling here, so we don't expect it to be exactly the same thing. And you can see, by the way, what would happen if I used a different F ratio distribution. Here I use 5, 4 instead of 4, 3, and you can see it doesn't match as well. The numbers start to go off significantly. And in fact, if I do this, let's suppose I say, look, take n from a chi-square distribution of 4, and take m from a chi-square distribution of 3, and divide your n result by 4, divide your m result by 3, and that's our transform distribution, and it's smart enough to know, hey, that's an F ratio distribution with first parameter 4 and second parameter 3. So I think I'm going to leave this as an exercise for you. But in conclusion, what you've seen is a tour of various distributions that we're going to be using throughout this course. I hope it reinforces your understanding of what a distribution is, what various functions like PDF, CDF, survival, quantile, all that stuff is. And we're now really laying a solid foundation for our understanding of statistics.